So the second part of week 2, we're going to talk about circulation, predominantly atmospheric circulation. We'll talk a little bit about ocean currents. So this circulation is set up by the difference between warm air masses and cold air masses, and it's really based on this idea of air pressure. So air pressure is just the weight of the atmosphere over the surface of the Earth. So at sea level, the Earth is about 14.7 pounds of pressure per square inch. So if you were talking about the amount of air pressure on the top of your head, it's about 401 pounds of atmosphere. And we measure it in millibars, and a millibar is about 0.014 pounds per square inch. So when we measure air pressure, we use a barometer, and it is measuring the effects of air pressure on this instrument that pushes a column of mercury up if it's or lets that column of mercury drop. And so low pressure would let the column of mercury drop because there's not as much pressure on that, and low pressure is anything below 1,013 millibars at sea level. High pressure is anything above that. And the reason, and then that back to this image, you want to remember that pressure decreases as you go up in the atmosphere. There are fewer columns or fewer molecules in the atmosphere, so that it gets colder as you go up. There's also, due to that, lessened pressure. When we look at pressure systems, you need to think about high pressure and low pressure systems. So a high pressure system, air is going to move from a high pressure to a low pressure, and it's a lot like putting a hole in a balloon. The balloon is under high condensed pressure, and when you put a hole in it, it creates wind, or moves from that area of high pressure, equalizes to low pressure. And air pressure systems move the same way. So if I have a high pressure system, it's going to push or move into an area of a low pressure system. So when we look at atmospheric circulation, you need to think of 4 major controls on that system. One is gravity. Hot air is buoyant, cold air sinks. The other is the pressure gradient, so how things move from a high pressure to a low pressure under the effect of gravity. The Coriolis effect, and then friction, which is a bit of a modifying effect. So basically this idea is that heavy things fall under the weight of gravity, under the effect of gravity, and that cold air systems are heavier and denser than warm air systems. So if you have a hot air system and a cold air system, the cold air system can move into that hot air system, causing air movement. So it really makes me think about the idea in Oregon. We have a lot of houses that have ceiling heat. Hot air rises, so why do you need heat in the ceiling? You need floor heat. Kind of a crazy idea. Okay, so the second control or driving force for circulation is called this pressure gradient. Okay, so again, high pressure systems means that there is a lot of force. A lot of force, and the air spins out and is pulled in to a low pressure system where the air then is moved up into the atmosphere. And this movement of air can be seen on weather maps. Let's see if I can move that term here. I can scoot that over a little bit. And on lines of equal pressure, we show those on weather maps with lines called isobars. So here you can see the millibars of pressure, and you can see all along that high pressure system the barometric pressure is the same, and its high pressure system is moving into a low pressure system. And you can see that where the high pressure system isobar lines are far apart, the weather is pretty gentle, it's not changing very rapidly, but where these lines are very close together, it creates a pressure gradient which causes air to flow and to move. The third driving force is the Coriolis effect, and this is due to the spin of the Earth. The equator moves faster than the poles because both of them have to make one revolution in 24 hours. So there's a couple links and really nice videos that kind of show this. But this makes parcels of air seem to deflect in one direction or other, beginning to create curves in storms, or curves in atmospheric parcels, air masses. So take a look at that, and I think the videos are really helpful for that. The fourth force is called friction, and friction happens mostly at the surface of the Earth, and what it does is cause the air parcels or the wind that's moving over to be slowed down as it runs into mountains, trees, buildings, and that also creates more of a curve or a spin. So you have all of those forces, gravitational force, the pressure gradient, the Coriolis effect, and friction that cause this whole circulation process. When we talk about cyclones and anticyclones, or converging air versus descending air, we're going to look at cyclones first. And this is the effect of air rising. So air can rise because it's pushed into a mountain and gets pushed up the hill. But whatever happens with air as it comes into a low pressure system and moves up into the atmosphere, it cools and expands and causes condensation or cloud forming. So cyclones are converging air masses at the surface that move aloft, and these are the kinds of systems you see when you see cloudy days or tornadoes or thunderstorms. Anticyclones are the opposite. Anticyclones are areas of diverging or descending air. So the air under high pressure systems descends onto the surface. It expands as it warms. It takes up any atmospheric moisture, so you get clear, sunny days, very stable weather systems. And we'll talk about that more in detail when we get into weather and climate. So we're back at this idea of the global circulation system, where we have a net gain of heat along the equator, and then this less radiation at the poles. And so how do we understand how does that energy get distributed using circulation, cyclones, and anticyclones? Well, there's 3 circulation cell model description that really talks about how that excess heat gets taken up and moved from one area to the other. And this is a model that shows these different this different 3-cell system. One system called the Hadley cells is on either side of the equator. So here is a Hadley cell on the southern hemisphere. Here's a Hadley cell on the northern hemisphere. Here's the mid-latitude cell, and here's the polar cell. And along the intertropical convergence zone, air masses converge, and because of the excess heat, those warm air masses rise up into the atmosphere, and as they cool, they create a lot of precipitation and clouds. That's why you get a lot of rain over the tropics. And then the air masses split, Some of the air moves in the upper atmosphere south, some of that air moves in the upper atmosphere north, and as it moves it gets cooler and cooler, and it descends down at about 30 degrees north and south. Now when the air descends, it is very dry, there's no moisture, and this is what is associated with the large desert regions of the world. They're part of the descending air from the Hadley cell. The air then that moves down along the surface is called the trade winds, and in the northern hemisphere they're the northerly trades, and you can see that the Coriolis effect is bending them to the west, and in the southern hemisphere the Coriolis effect is bending those trade winds more to the east. The mid-latitude cells then start bending or following along the surface, flowing north until they hit the polar cells, which are a dense dome of cold high pressure. And these cells, these mid-latitude cells, are responsible for the westerlies, both in the southern hemisphere and the northern hemisphere. So it's really important to understand how the Hadley cells work, primarily the movement of those weather systems and the creation of deserts. So, we go back to this. And so really what it's doing is taking that excess heat along the equator at zero along the ITCZ, moving it up into the atmosphere, losing some of it as rainfall, but then moving the rest of that heat, distributing it north through that to the 30 degrees north and south longitude, and then taking any extra heat and moving it up from 30 degrees to 60. So it's that real very efficient distribution system. And then looking at let's see, did I do ocean circulation? That slides out of, there we go. So then I want you to look at just these basic patterns of ocean circulation. And again, cold water tends to flow along these cold currents tend to be very heavy and dense. They're also associated with a lot of fish and food sources. The warmer currents are lighter and more buoyant. They flow along the surface, and they create these ocean circulations, bringing warm water, which also impacts continentality and temperature. There's a video about the El Nino. I want you to take a look at that video and be able to look at that circulation system and how that has, whoops, let me move this silly thing here. That circulation system that, takes moisture from Australia and creates desert systems there, and then takes that excess moisture onto the Pacific, to the west coast of U.S. and South America, creating huge storms in that area. So make sure you take a look at that. And then the last part of this chapter is really looking at smaller wind patterns, land and sea breezes, how you have a day and night alterations of onshore and offshore winds as a result of continentality and the specific heat of water, mountain valley breezes, and then take a look at the regional wind patterns of monsoons and be able to talk about those. And I think those are pretty clear in the reading.